Hello, everyone. Please welcome Erik Hadland, Director of Technology Policy at the Semiconductor Industry Association and Moderator for today's discussion, to the stage. Thank you.
I'm the second from left.
Already good.
We have
Where our faces up there. So,
Alrighty, good morning. Well, it is my pleasure to be here with you today. Like Olivia mentioned, my name is Erik Hadland. I'm the Director of Technology Policy at the Semiconductor Industry Association. It is my pleasure to be joined by some esteemed panelists. I'm very excited to have a discussion with each of them. I'll invite them up onto the stage now, and they can provide an introduction for themselves. While they're getting seated, this is the fun panel. You're going to hear a lot of conversation today about the nuances and current issues of AI, and we have a space now to think beyond that into what is not possible yet, but will be possible tomorrow. The video beforehand stated that we're going to build beyond the limits of what's possible. Everything is only impossible until it's not, and we have some folks who are working at the edges of what's possible today. This is the age of AI. But in many ways, we are at the very beginning of a much longer story. There's a lot that AI can do, and there's a lot that AI still cannot do. AI is a hardware-limited problem primarily, but there are limitations throughout the entire computing stack, and we'll talk about those. At the Semiconductor Industry Association, we did some calculations recently. Our revenue last year was somewhere around $525 billion for all chip sales globally. And by the end of this decade, we'll reach over $1 trillion. The demand drivers to get us there: electrification, electric vehicles, autonomous and driver-assisted systems, and primarily AI. It's my pleasure to be up here with these four panelists. I'll ask them to introduce themselves and give an introduction to their organization, and then we have some questions to get us started.
Hi, hope you're awake. All right, good morning. Good morning. Perfect. Getting a little bit, there we go. So I'm Johnathan Ross. I'm the CEO and founder of Grok, and I think we're still getting a little bit of echo. All right. We're good? Okay. All right. So we build inference chips. What is inference? Well, when you train a model, that's when you create it. It's sort of like designing a car. And when you do inference, it's like producing the car. So at Grok, we build chips that do inference much faster than any other chips. If you go to our website, grok.com, you can try it right now. My background, I started the Google TPU, which is their AI chip. And the reason that I started Grok was the realization that Google had a lot of AI, but didn't have enough compute. What was the world going to do? We weren't going to be building chips for every single company. So I wanted to build chips that everyone could use. And in the last 8 weeks, we've gone from fewer than 10 developers in our private beta to over 145,000 developers, which I think makes us the fastest growing developer platform in the history of all developer platforms.
Whitney Mason. I'm the Office Director for DARPA Microsystems Technology Office. DARPA stands for Defense Advanced Research Projects Agency. What DARPA tries to do is to be at the forefront of research to create the next disruption in technology. I might argue that some of the technology that DARPA MTO developed 60 years ago formed the basis of the internet, formed the basis of the current AI capability. What DARPA MTO wants to do next is to create the next disruption that changes the way we think about doing activities to include AI, but beyond AI.
Good morning. First, I want to congratulate Illy and the whole team at SCSP for really organizing this incredible event. I think the pent-up demand here is incredible. Washington really needed a big AI Expo, so I think it's pretty exciting. So I'm the Vice President of Worldwide AI Initiatives at NVIDIA. You may have heard of us. When I joined the company 5 years ago, the world was still pretty convinced that NVIDIA is just a semiconductor company that makes chips. But that was never Jensen's vision. He hasn't pivoted from his vision. It's been the same vision for 30 years, which is that the world needs a new kind of computer, a new kind of computing platform called accelerated computing. And that's a full stack platform, hardware and software. And NVIDIA has been building and perfecting and improving that platform for multiple decades. So it looks like an overnight success, but it's not quite. And now today, of course, almost everyone knows who NVIDIA is, but still, it's we're still in the very early days of this revolution around AI, and there's lots of room for innovation and competition, and I think that's good for the world. My job at NVIDIA is primarily to work with the nations of the world to help them understand and to build out the sovereign infrastructure that they need to support their national AI ambitions. That's become kind of an interesting dialogue recently, but actually we started down this journey 5 years ago to really having conversations and helping countries think through not just what AI means to them, because frankly, most countries had a strategy already, but they didn't think through the infrastructure they needed to actually realize that strategy. That's a more recent conversation. And now it's become almost a global imperative to invest at scale in countries in support of their sovereign objectives. And that's obviously an exciting time, both for the US and our allies. And that's my primary focus.
Good morning. Can you guys hear me okay? Well, my name is Ziad Asghar. I'm the head of AI at Qualcomm and also lead other technologies, like camera, graphics, and everything. When we look at AI, we think about AI as a technology that's truly horizontal. It grows across all our products and also goes across all the different technologies. It makes the camera on your phone better. It allows you to be able to see in the darkest of rooms. And that precisely is my charter, to actually take AI and bring it on to the device. Devices that fit in the palm of your hand. And with that comes some additional benefits, right? We are used to, having these smartphones that are not plugged in. But if you could, let's say, run a 10 billion parameter model, you could run a ChatGPT-like experience. You could do multimodality on devices like your phone, in your car, on an AR, VR device, on your laptop. That's extremely limited in many capabilities today. But we are launching new products that actually have AI inherently built into all of these devices. And with that comes the added benefit of things like privacy. If the processing happens entirely on the device, if that inferencing implies that the data never leaves your device, it's private. You don't have to worry about it ever going to the cloud. So there's some amazing benefits that come with that. Also, with Qualcomm's pedigree, we are used to talking about milliwatts of power, not hundreds of watts of power. And I think that brings in a lot of advantages as well. So we'll talk through a lot of those. So that's my main charter. And we're actually already seeing that. We have customers that can do ChatGPT-like experiences on their phones and on their PCs today. And we expect that capability to continue to grow and scale as time goes by.
Is this on? Oh, wonderful. Excellent, Ziad. Thank you very much for kind of describing that as a horizontal problem. I think you're absolutely right that this is a challenge for a broad swath of the semiconductor world and even beyond as well. Before we get to that, and we'll talk some more about that in a bit, I want to go straight for a hardball question here. Since generative AI was released to the public, energy demand at data centers has spiked, prompting some conversations, well-warranted conversations, about the sustainability of AI scaling. How do we solve this problem of rapidly growing energy consumption to support AI? Whitney, I think you have some concerns about this and maybe some good thoughts to get us started.
Hello. Thank you. Thank you. So we've been talking a lot about energy consumption of microelectronics in particular in the office and talking to a lot of collaborators. And a lot of people think about AI processing from a lower the power per device. And DARPA MTO has invested in a lot of programs, analog computing accelerators, things like this, that reduce the amount of power per inference, power per compute. But what we see though is that the more power, the more efficient your devices are, the more inferencing people want to do, right? It's people talk about the insatiable demand of AI, and that is just a word that makes us uncomfortable. So we want to think about this from a different perspective. How do we think about actually reducing the amount of power that it takes to do things? By doing things like recycling the power from the chip. A data center creates an enormous amount of heat, right, that we actually have to mitigate by using more power. What if we could capture this heat and put it back into the system so that I could actually do more operations, more inferencing, more training with the same device. I think this is critical for us to think about this because nobody's going to stop wanting to do more. And we should enable the possibility to do more without having to spend the world's power supply on creating the energy to do this.
Are we on? Good. Yeah. You know, you asked us to dissent, but I don't want to be disagreeable to my fellow panelists. But I do want to suggest that maybe we're not asking the right question. It's easy enough to just call it an energy crisis, but I think that very much depends on in what country you're sitting in and where you sit in the value chain. There are countries that have a power advantage and countries that do not. And depending on where you are on that spectrum, the energy challenge is an opportunity, right? So some countries, because of the natural advantages in terms of their infrastructure and geography, will actually be in a position to export not just energy, but even computing, right? And go back 20 years ago, as early as 2004, the engineers at Google were talking about computing, not just about a chip or a machine, but at the data center scale, right? Data center scale computing. And you do have to think about both the performance and efficiency, energy consumption at that level. And you have to optimize for every aspect at that level. And from that perspective, again, innovators, pioneers have advantages on that. So it's a crisis for those that don't think about and plan ahead. And we are definitely, we're never going to go backwards. The AI consumption is going to be up and to the right forever, right? We want to optimize the size of models. We want to optimize data sets. So there's a lot of data science innovation. There's a lot of chip innovation. There's a lot of data center design innovation. But ultimately, it's an opportunity as much as it is a challenge. And I see countries, as I go around the world in my role in NVIDIA, I see a lot of countries positioning themselves, again, to capitalize on their investments and their planning and infrastructure. They're not everyone is equally threatened per se, but on a global basis, you know, we have to optimize and focus on sustainable computing, the most sustainable computing that you can, you know, for the different kinds of workloads that you have. There's no one easy answer to that. I mean, everyone wants a headline, but this is a very complicated story, right? So there'll be lots of clouds and lots of chips and lots of workloads and lots of data centers, and there's going to be a different model for optimizing all of those. And ultimately, I think that the innovation in the industry has to be matched with innovation in government to work together to achieve that goal.
Maybe I can, we take a little bit of a different approach with this. I think we think of hybrid sort of AI inferencing. What I mean by that is that you have intelligence that's built into all the different parts of the network. Essentially, you of course have a lot of inferencing that's happening in the cloud today. You also have inferencing that can happen on each and every device that's closer to the user. Data is actually generated close to the user, which is on a smartphone or on an AR, VR device. So you could actually do a lot of that processing over there. Now, if you come from the perspective of not just being able to do those processing on the device, but also doing it at lower power to be able to do more domain-specific models that have curated data to be able to make them smaller. What we're also seeing is when the models start, a new topology or a new modality comes in, the model is fairly large. When ChatGPT-3 came out, it was 175 billion parameters. But as we've seen Llama 2 and Llama 3 come out, there's 7 billion parameters, 8 billion parameters, 13 billion parameter models, but still fairly competitive in the sense of how they are able to perform compared to ChatGPT. So the model improvement, the algorithm improvement, just in terms of tech, is also making it more possible for us to be able to do it in a more energy efficient manner. There is a sustainability argument. There was a paper that was recently published that talked about the fact that to do a single ChatGPT session, a graphics-based solution takes like a bottle of water worth of cooling. So there are indeed challenges, right? And what we see is the number of users who want to use generative AI, the number of use cases, and then just the sheer number of and size of the model continuing to grow means this problem will exacerbate. So we need to, of course, focus on techniques that allow us, some that I mentioned today, to be able to make it happen. And we think one of the capabilities is to be able to take some of that processing onto the device. It gives you privacy, it gives you other benefits in addition to the benefit of energy conservation as well. And I think that is what's going to make generative AI really reach its full potential. By moving it to the device, you also democratize these experiences. Just think about it. When the web browser was just on your PC, it was limited to a certain number of people. As it came to your smartphone, billions of people have access to it. I think it's very analogous in my mind. And I think we're going to do the same thing. And with the energy benefits of on-device that Qualcomm has focused on, We have done different precisions. We have done quantization. We can prune the model. You can compress the model. There's distillation, lots of techniques to be able to make the model more efficient that we have already done and others are looking at too.
Jonathan.
All right, here's the dirty little secret. Energy efficiency is a choice. Follow the money and you will know exactly what's going to happen. So let me give some examples. I'm aware of some data centers from 5+ years ago where, since it's cheaper to buy power at a constant rate, they would install giant metal resistors in the data center to make sure that they always used the maximum amount of power being delivered to that data center, because it was cheaper than having to build the infrastructure to have a variable amount of power delivered. So why is it that people are currently using so much power for GPUs? Actually, the GPU vendors have some of the best engineers in the world. They could make it dramatically lower power. So why are they using so much power? Well, when you buy a GPU, they're typically margined up for the data centers about 80 to 90%. That means that you are paying almost 10 times as much for that GPU as it costs to make. As a result, the economics on the power almost don't matter. Now, if you increase the voltage of a chip, you can increase the frequency and you can squeeze out a little more performance. So if you're paying 10 times as much for that hardware, then you're willing to pay 10 times as much for the power, or up to, in order to get a slightly better performance out of it. The best thing that you can do for power right now is to drive down the cost of computing from the CapEx side, because it forces people to pay attention to the OpEx. Even 1 year ago, no one was talking about power efficiency, or they were all talking about it, but no one was doing anything about it. We would go in, we would show how power efficient we were. People would go, that's great. And then they would look at the total cost, and that was the only thing they made a decision on. What's changed is there isn't enough power in the grid today. You can't get it. And as such, people are starting to finally design around it. So one of the most important things in terms of power and energy efficiency is sort of collecting up a bunch of jobs and doing them together. Actually, data centers use a lot of power, but they reduce the total energy, sort of like a freight train. It may use more power than a moped, but it uses less energy to transport things because it's all bundled together and you're moving it all together and amortizing the cost of moving that freight train. So what we need to do is we need to set the incentives economically to reduce the amount of power used, and everything will follow.
Certainly sounds like a problem for policy in Washington. Thank you, Jonathan, for that. I wanted to, for many years, the quest for more capable computing was the quest to make a transistor smaller, so you can smash more of them onto a chip and get more performance out of it. But Ziad, you mentioned that this is really a horizontal problem, and certainly there are elements that need to improve for power management, optical connectivity, things of that nature. What are some of the other areas we need to improve here beyond just the advanced logic elements of AI?
I think there is a lot of new techniques that are coming in. We of course know there are some challenges at this point in time with Moore's law. And there are a lot of techniques that the industry is working on. For example, to be able to have different chips that are done in different nodes, and then to use techniques like die-to-dies and chip-to-chip to be able to stitch them together, to be able to bridge a lot of those challenges as well. But I think in addition to that, sometimes what's overlooked is software. I think AI software is absolutely critical. And I think it's probably the larger challenge today also in a great way than the hardware. I think it's important to have the best-in-class compilers. It's very critical to be able to have techniques that allow you to be able to leverage that model, but run it in the most efficient manner on your hardware. I think that's another part that's sometimes overlooked. So the problem is manifold. It's many different levels, right? You have to have the best compiler technology. You need to have the best ML ops. You need to have the best hardware. For example, in our side, we have multiple engines on our devices that can do AI inferencing. You can have the CPU that can do AI inferencing. The GPU can do it, but you also have something called the neural processing unit, an NPU. So you need to have multiple different engines depending on the time of workload, depending on the use case, depending on the latency. You can actually choose the most appropriate engine to get to the best power consumption, but get to the best KPI as well that that particular use case desires. So let's take an example. If you're talking about doing ADAS, which is driver assist system, the latency requirement on that is going to be very, very critical compared to what you might have for, say, language translation or for summarization. So each and every use case requires a different engine. From a smartphone perspective, the architecture that we always focused on is an architecture of accelerators. That's the best way to be able to get to the lowest power possible, because you're not running the workload in one large general purpose engine, which consumes a lot of power. So I think, like I said, each and every different level of the stack, there's a different challenge and different solution that the industry has to look at.
And I think we're hearing more and more these days about this process of co-design and getting different parts of the ecosystem to work together so that the solutions are tailored to one another. Whitney, anything you see early on in the pipeline from your perspective at DARPA for any of these developments?
Hello. Thank you. Yeah, thanks. So one of the things, first of all, totally agree, right? Building hardware to do the math that you want to do, I think, is critical to optimize performance. And we're starting to look at things like quantum computing, right? Quantum computing is not good for everything, despite what a lot of quantum computer companies say. But it's really good for certain calculations. Think drug discovery as a great example. We've been looking at biological compute, actually, as well. Can we integrate biology and electronics together? Biology is slow. It's not going to be low latency. But if you can collapse 10 to the 4 operations down to 1, then maybe it doesn't matter. And so there's some research in the world that says that biology is good for certain math capability. We have an effort right now to build a hardware for fully homomorphic encryption hardware to make it much faster and make it appropriate eventually to go into your handheld device. And so we do believe very deeply that we have to tailor the hardware to the math. But we want to think about getting away from just using silicon and transistors and moving out into other spaces in the world.
But yeah, I just wanted to double click on this idea of software, because I think I wanted to dimensionalize it a little bit. You know, there's different layers of software here that matter, and in each one of them lends a potential for significant innovation. And so going back to your comment, Ziad, that's right. The new model for growth is not just hardware or manufacturing innovation. That's still happening. We're still squeezing some more transistors on chips, but and there's advances in both packaging and material science that's promising on the hardware side. But it's really the silicon times the software times the system, right, that ties it all together. And so now you have these three dimensions of performance innovation. And software innovation, unlike hardware innovation, software innovation is nonstop, right? It's 24/7. You can roll out updates to your phone. You can roll out updates to your computer. But people have to remember, it wasn't that long ago that supercomputers, the infrastructure for AI, right, were pretty much a science project, every single one of them, right? I mean, I'm sure you know this going back to your career. I mean, there's only a few hundred of them in the world. And every one of them, basically have the custom-built software, very bespoke science projects, essentially. You use some open source, some custom-built, but these are not commercial platforms per se. But the industry is evolving very fast. And I know at NVIDIA, and other companies are trying to really take that stack that sits on top of that system, not just what's on the chip, but the whole end-to-end system, and really, innovate on that so that the performance, again, it's not just the chip performance, it's the whole data center as a computer performance, right? So if you look at the innovation from the silicon straight through the system and all the software layers that are running on top of that, there's just an opportunity to innovate at a scale that we've never thought of before. So yes, we used to roll out a chip every 2 years. Now we're rolling out a chip once a year, right? But software is every day, right? Innovation. So if you're doing everyday innovation times every year innovation, now that's a hockey stick, right? So I think that's the new curve.
I heard Bill Daly last summer give a talk who's the chief scientist at NVIDIA, give a talk at DARPA's ERI Summit and described that where they're finding the most benefit is actually not just in transistor node progression, but is actually in this tailoring the hardware to the math, working with all the different levels of the software stack as well. And that's exciting. You're right, hockey stick effect there. We've spent a lot of time talking about the energy consumption from AI, but how is AI going to help us solve problems of energy demand just beyond computing? What is this going to enable for us in terms of reaching our climate goals faster? Or scientific and discovery?
All right. I mean, I just want one example that I always thought it's just a really, really good example. The first off, there's not enough time to answer that question at the scale that we should, right? I mean, there's a really long narrative on how AI can be used, but when it comes to both energy consumption and say just climate change, right, and the intersection of that with AI, the one of the most profound examples is just sort of both climate prediction and weather prediction sort of intertwined, but they're not the same thing, right? You want physics-based simulation at a certain level of granularity and resolution to actually understand the current state of the climate and then to predict out over many years. And I don't know that we actually have enough engineering innovation or enough computing in the world today to even do that. But it's something that we're very, very desirable to do. Both NVIDIA with our Earth 2 project and also the European Union with their Earth project as well. There's a lot of digital twin efforts happening, and actually everyone's working together, so they're not isolated projects. But being able to do that is one of the North Star. But what's happening right now, and one really exciting innovation that I think went back as I think it was first published in 2022, is to move away from numerical weather prediction, right, forecasting, and which is basically brute mathematics, and to start really harness AI, which is not happening today. The vast majority of weather is not using AI, right? But the implications are huge. So the ability to predict down to unbelievable resolution at unbelievable speed and power efficiency is dramatic. So if you read the paper on Arbix, so they're able to make extreme weather predictions 45,000 times faster with 12,000 times less power using AI, using the Fourier net model. And I mean, these are just hard to even fathom scale of difference. But this is the kind of innovation that AI will bring to something as like the prediction of flooding and other kinds of extreme weather events, which then will set the foundation for ultimately physics-based simulation for climate prediction.
I can take some. So especially on device angle, we see a lot of use cases that are truly amazing. So one of the ones that I'm really personally interested in is from an education and a healthcare perspective. So if you think about it, a class full of students, and each has a device in front of them, and they're actually going through their lesson plan. For the most part, with a camera on the top, you can actually tell, if you ever taught a class, you can tell if a student is getting the material or not. You can actually tailor that academic plan on the fly using generative AI to be able to give instruction to the student and at the pace where each student can get it, right? It's a great application for being able to get material to the student at the right pace. Another one, many of the countries today, they are facing, aging populations. So what you could do is essentially have a device that's sitting in their home that's able to get all the sensory data coming from them. And at the same time, it's actually able to assess that an event is about to happen rather than for it to happen and then somebody come and help them, right? So essentially, there is a lot of benefits like this where you could actually be, in the long term, actually perhaps modifying the plan or alerting a healthcare provider that there is some such condition that's developing. At the same time, from a productivity perspective, I look at generative AI as a true force multiplier. For this discussion, let's say you could have actually automatic transcription. It can give you a summary of this event. It can create 3-point, slides of the discussion that we just had. It just allows you to be able to do more work in a given amount of time. And the true, I think, power of all this is we feel is with the on-device angle, you can actually personalize these experiences. So that large language model that's sitting on your phone, with time, you can fine-tune it to my accent, or you can change it to the words that you use. So we envision that with time, that becomes the golden LLM model for each one of us. And I think that's where the true power of generative AI will come through.
Great. Jonathan.
So AI is not a solution to climate change. AI is a tool. Climate change is an economic problem. It's the tragedy of the commons. Some of us have benefited from burning coal for a while, and it's bootstrapped our economies. Now other economies want to do the same thing. That's the problem. So I feel like whenever we talk about AI and climate change, we're sort of deferring the problem and hoping that AI is going to come in and solve it for us. We have to solve it ourselves.
So this is totally off topic. I love the fact that you said training, teaching students. One of the biggest problems we think that we face from an innovation perspective and an advancement perspective is people. If you read the literature, it says that due to the CHIPS Act, we will be 300,000 people short in 2030 for people to fill these boundaries in order to create the new advancements for our country. Now, I think Ziad said, right, you can automate some of these things and you can have AI start to do your innovation for you. And that may be true. That leaves a little bit of a pit in my stomach, frankly. I have this vision of this dystopian movie, right, 50 years from now when everything breaks and the people have no idea how to fix anything. But I think that leaning on AI and leaning on some of these tools to enhance our workforce is great, but don't forget the hardware, right? AI is sexy, and you can innovate every day, and it's relatively less expensive to transition your software than it is hardware. But I will argue, with acknowledging my bias, that it's the hardware that actually enables the AI to do what it does. And so, as you're going through life, think about how you can encourage your children, your neighbors' children, the community in which you live to actually try to innovate on the hardware as well, because this is an important part of innovation and of security for our country and economics for our country.
I think one of the primary areas of innovation that we're seeing is this building up capabilities at the edge, and even AI at the edge. We're throwing more and more of the compute workload toward the edge for benefits for latency, energy, efficiency, things of that nature. What role do you think AI at the edge is going to play, and what are some of the applications you're most excited about in this space?
I would probably challenge that, so I should probably go last.
I invited dissent before the panel, so I'm glad folks took that seriously.
Yeah, sure. Yeah, I think I'll talk a little bit more about it. I think there is a lot of benefit that you derive by doing it on the edge. So one of the aspects I talked about democratizing this generative AI experience, right? So now talk about 6 billion people who are being able to leverage and to be able to use these capabilities. Well, somebody has to pay for that energy that we were talking about in the first question, right? Whereas if you do it on a smartphone, you just pay for that smartphone once, and subsequently it is free. And free is a great price for doing a lot of these use cases, by the way, right? So we do envision that there is a benefit that it brings to the people, and in many cases to those people who most need these capabilities, in my opinion. Now, you can imagine that you have a virtual assistant on your smartphone. Now, today, just to take an example, right? You want to schedule a lunch with a friend. So what will you do? You'll go to OpenTable, you'll do the reservation, you look at your calendar, you figure out what time works, you go to your text message to figure out when he can come, you look at Yelp to look at the reviews. But what if you could go to your virtual assistant on your smartphone or your PC and say, well, schedule a lunch for me with my friend X tomorrow. It goes to your calendar, it goes to Yelp, it goes to OpenTable, it goes to the SMS message and does it for you. So it's, I think, the utility, it's the benefit, it's the convenience of doing a lot of these things. But like I said, it's a force multiplier in my mind. It basically allows you to be able to do more work in lesser amount of time. And I think that's the true promise of generative AI. And that's why I strongly feel that the center of gravity of generative AI will continue to move towards the device. Now, let's take the example. Cloud does not know your calendar. You don't want the cloud to know your calendar in many cases. I don't want the cloud to know who did I just send a text message to. So if I can do this on the device, that's when I bring the benefit of privacy, right? Now that statement and that information has stayed on the device. But guess what? My device also knows what do I like. It knows what my age is. So let's say if I say today, hey, what should I do in the next 3 hours? I'm free for the next 3 hours. If you ask ChatGPT, it will tell you the same answer if you ask or if my 10-year-old son asks. No difference. But if the device knew who was asking that question, you could actually answer the question based on what was needed. And I think that's the true promise of on-device. So we're super excited about it.
Yeah, that's great.
So I work for the Department of Defense, and everybody gets all excited about the device in your pocket. But the United States Army was the first original carry things around people, right? When they were big and heavy and bulky, and provide relatively little capability. But this is a huge need for them, and it goes beyond. Scheduling your lunch, right, for real capability out there. And there's lots of use cases that to enable them to see further from a sensing perspective, to be able to communicate not just well and at depth, but securely. There's the need to understand the environment, which goes to the compute. We also have the added need of having security. yes, when you're remote, your information is on your pocket, but you do have to connect to the internet sometimes, and you do have to connect with other people's internet. How do you make sure that that information stays private and you can't reveal somebody's information or critical mission data? How do we operate in extreme environments? The United States military goes underwater and we go to space, and our electronics have to operate over that extreme environment. And so there's lots of things that build upon what the community does, but the military, the Department of Defense needs that extra capability, that added security, that added trust. I'm sure that lots of people at this conference will be talking about trust in AI, but how do I trust the answer that I'm given? So new use cases and not just doing things that we can do today, but allowing us to think about what's possible that we can't do today.
Johnathan, please.
All right. So when we first started Grok and we were fundraising, one of the questions that venture capitalists would ask us is, everything going to move to the edge or is everything going to move to the cloud? And the answer is both. Like, we've seen this happen for the last 20 years where more and more is being done on edge, but more and more is also being done cloud. Who here uses search that runs locally on their devices? I see two hands. Okay. The reason that you do it in cloud is because the more compute you have to apply to the search, the better the result that you get. So if it takes less effort to move the data to a data center and then do the computation, you will almost always do that. The reason that you do things on device is for when you don't have great connectivity. And that can happen, especially in combat situations. It can also happen when you're driving far outside and you just need something to work. But when it comes to energy efficiency and cost, there is no such thing as a free lunch. That phone that is in your pocket, that chip that is in your phone, it's sitting there idle most of the day. That silicon was fabbed to be used less than 1% of the time, whereas silicon in a data center is used almost all the time. And some of those trade-off decisions that can be made in the design, there's this one where you can make transistors use less energy for the compute if they burn more power while they're on. So when you use those transistors in a data center, you actually use a lot less energy, even though you use more power for each unit of work. So bottom line, you're going to be using both edge and cloud forever. You're going to want to do as much as you can in cloud. And whenever you can't do it in cloud, where it's more efficient and actually lower cost, you're going to want to move it to edge because that's the only thing you have.
Yeah, I'm glad you brought up that point about the use of how much time chip is actually in use at a data center. I saw a study recently on embedded carbon for different types of silicon products, and in a data center, the use is constant, and so the embedded carbon for that device is actually skewed much heavier toward the operating life, and much less of that embedded carbon actually comes from the fabrication process. It's almost entirely reversed for consumer electronics.
By embedded carbon, what you're saying is there's a carbon footprint for building the device itself, and you have to factor that in, and that can be extreme. A modern fab can use a gigawatt of power.
Great. Well, let's see here. There's a lot that we weren't able to get to in the discussion today, but just in closing, I'll finish with where I started. We're at the beginning of a very long story with AI, and it's certainly going to have lots of exciting chapters along the way. As was mentioned by Johnathan, this is a tool. This is a powerful tool that we're going to use not only to define our economic and national security, but also our productivity in the workplace and scheduling lunches with our friends, and for discovery and scientific innovation. And certainly this is among the most powerful tools we've seen in decades. There are very few facets of life that the generation of AI is not going to impact, and some of those in the very, very near future, even today. Whitney, Keith, Ziad, and Johnathan, thank you very much for your insights and helping us to consider what that future looks like.